Okay. So, this is the 3-phase NPC circuit, and let us now understand the operation of this circuit in details. In order to understand the operation of the circuit in details, we take only one phase of the converter and analyze it in detail, so that we can also understand the other phases. Other phases are identical in operation. So, we have taken here one phase. So, first of all, let me clarify, this is a DC bus voltage which actually is split into two parts using this capacitor. Okay. So, the midpoint of these two capacitors is what is being accessed by the converter. So, there are no two separate DC sources, but the DC source is split into two parts using two capacitors and the midpoint. Now, how does this converter operate? So, let us first take the case when the current I is going out through the terminal A. Okay. Let us take this case first. When the current is going outside out of this converter, and we would like to get a voltage V d by 2, okay, the voltage V A O, the pole voltage V A O. So, everything is now accessed with respect to the point O, which is assumed to be at 0 potential. So, V A O, the voltage is equal to V d by 2, and the two transistors S 1 and S 2 are conducting, and then we get V d by 2 voltage at point O with respect to point A with respect to point O, as you can see here, V A is equal to V d by 2. The S 1 and S 2 are on, okay, and these are the two devices conducting for the current going out of the terminal A. Okay. Now, when we want to get a 0 voltage, what happens? When we want to get the 0 voltage, we turn off the pulse to S 1, okay, while keeping the both the pulses for S 2 and S 3 on. So, let me clarify it, that if I want to get the 0 voltage and the current is also going outside, what can be the possible path of the current? The possible path of the current can be like this, D 5 and S 2 and going out like this. So, this is the possible path of the current if the current assumes this direction, and assuming that if there is no drop on D 5 and S 2, that is these two devices are identical, this means point A here will be shorted to point O, and so we will get a 0 voltage. Okay. So, therefore, in order to get 0 voltage, what we can do for a positive direction of current as shown, what we can do is the switch S 1 has turned off and S 2 can be kept on. When the transition is happening from this to this, S 2 can be kept on, and then the current will flow like this here, okay, and we will get a 0 voltage. Okay. If we want to get the negative voltage, then what we will do? Suppose the current direction is positive and going out here, we will give pulses to S 3 and S 4 together, okay, and withdrawing pulses from S 1 and S 2. Okay. If we give pulses to S 3 and S 4, then the two diodes D 3 and D 4 will start to conduct here, because the current direction is as shown. The current is controlling, the direction of the current is actually controlling which devices are turning on at a particular instant. So, in spite of giving the gate pulses to S3 and S4, the diodes D3 and D4 will conduct, and the pole voltage A with respect to point O will be minus V d by 2, because the diodes are ideal. So, this will be minus V d by 2, and so this is the third row in the table. Minus V d by 2, diodes D3 and D4 will turn on in spite of the fact that S3 and S4 are given pulses. Okay. Now, let us see what happens when I is less than 0. This is shown in this figure. Okay. Now, when I is flowing into the converter like we have shown, suppose we want to get V d by 2 voltage. So, we would like to have, so what is our aim here? We would like to have V d by 2, 0 and minus V d by 2, these three levels of voltages between point A and O. This is what we desire, and the current through point O should be bidirectional in nature. It is an AC current. Okay. It can be going out through the A terminal or it can flow inside the A terminal. So, suppose the current is now flowing inside to the converter, and during that time if I want to have the plus voltage on point A or plus V d by 2 on A with respect to point O, then what I will do? I will give pulses to S1 and S2, but since the current is going inside, what will happen is the diodes D1 and D2 will start to conduct, okay. And therefore, I will get, since the diodes are ideal, I will get VAO voltage to be plus V d by 2. It is shown on this row here. Now, comes the condition, this is tricky, now comes the condition 0 voltage. Suppose the current is going in and I want a 0 voltage VAO. What will I do? What is actually the path of the current? The path of the current is, so I will turn on S3, okay, and the path of the current will be something like this. Here it will come in like this, go through this transistor and go through the diode and come to the point O. Okay. So, during this point of time I will get 0 voltage VAO with the switches S3 and D6 conducting. So, that is what it is shown here, S3 and D6 are on in this table. Again, if I want to get the negative voltage, then I will turn on S3 and S4, I will give pulses to it, and then the current will flow like this. The current is inside and it will flow through the two transistors S3 and S4 as shown in the table. So, summarizing what we can say? We can say that if I want to get the voltage VAO to be V d by 2, okay, give pulses to S1 and S2. Okay. Means comparing this figure with along with this figure, I can say that if I want to get VAO voltage to be equal to V d by 2, then give positive gate pulses to S1 and S2. Okay. Do not give pulses to other switches. If the current direction is positive, then S1 and S2 will flow, will conduct, whereas if current direction is negative, then D1 and D2 will conduct. So, the current will decide which devices will conduct. So, we will just give the pulses to S1 and S2. Okay. Now, next case, when we want to get the 0 voltage, VAO is 0, what will we do? What shall we do? We will give pulses to S2 and S3. We will give pulses to S2 and S3. You can compare this figure with also with this figure. Okay. I will give pulses to S2 and S3, withdrawing the pulses to other switches. Now, if the current direction is positive, then it will automatically make sure that D5 and S2 are conducting. Okay. D5 and S2 are conducting. Whereas, if the current direction is negative, it will automatically be ensured that S3 and D6 are conducting. Okay. S3 and D6 are conducting, because so when we want to access the 0 voltage, we just give the pulses to S2 and S3 simultaneously together. Depending on the direction of the current, either S2 will conduct or S3 will conduct, okay, and along with either D5 or D6, the clamping diodes. So, one of them will be conducting depending on the direction of the current. In both these cases, we will get 0 voltage. And similarly, if I want to have VAO as minus VD by 2, what we will do? We will turn on S3 and S4, or we will give pulses to S3 and S4. Okay. And so, if the direction of current is negative, then these two devices or the two transistors will be conducting, whereas if the current is in the positive direction, then the two diodes will be conducting. Okay. So, we understand that in this converter, all these 4 IGBTs or transistors or MOSFETs, if you use MOSFETs, all these will be useful, all these 4 transistors as well as the 4 diodes are useful, and together with D5 and D6. So, under different conditions of operation, some switches, one or more switches will be conducting, and you should be able to fully understand under what condition which device will turn on. Okay. So, another thing that I forgot to mention previously is like, where do we use neutral point clamp converters, because as I was discussing the IGBTs, so it came up in the mind that neutral point clamp converters, again it is a multi-level converters typically used in the kilovolt range and megawatt, hundreds of kilowatts to megawatt power range. So, 11 kilovolt they can be used, something like that, but not probably not at the high voltage DC transmission. At hundreds of kilovolts, this is not the most recommended converter. So, neutral point clamp converters are highly used in grid connected applications as well as motor drive applications. Okay. It is probably it is the most popular multi-level converter topology. Okay. But usually it is all limited to 3 level. Okay. We see that there are 3 levels of possible, 3 levels are possible from NPC, although people have proposed 5 levels, 7 levels like that, but it is not so popular. We will see that why it is not so popular. So, this is what the converter operation is, and this is shown for A phase, and we can also do the same thing with the B phase. and the C phase. Okay. So, this is straightforward. So, this is what we are summarizing here, and we see that based on the table which we have shown, we can see that in this converter S1 is S3 complement and S2 is S4 complement. So, these two switches S1 and S3 are given complementary switching or complementary pulses, whereas S2 and S4 are given complementary pulses. Okay. You can also understand in a slightly different fashion, like if you give, see, you need S1 and S2 to be turned on so as to get the Vd by 2 voltage. So, S1 and S2 cannot be made complementary. So, they are the same, means in order to access VAO equal to Vd by 2, I need S1 and S2 to be turned on. I cannot make S1, S2, S3, S4 all 4 of them turned on at the same time, right, then it will short the whole DC bus. I cannot also make S1, S2, S3 to be turned on the same time. Okay. If I turn on S1, S2, S3 at the same time, then what will happen is this way the DC bus will be shorted in this path here. Okay. So, in order to prevent that, I must turn off S3 when I am turning on S1. Okay. This can be obtained from the table given in the previous slides, but you can also see that how can we obtain this, like if you see, observe this converter S1, S2, S3, S4, you cannot turn on all of them simultaneously. Okay. So, then you will short this DC bus. Now, if I want to get the positive voltage, I of course will turn on S1 and S2 simultaneously. Okay. So, S1 and S2 cannot be made complementary. On the other hand, if you see that if I turn on S1, S2, S3 at the same time, okay, then what will happen is I will have a path like this, S1, S2, S3 like this here. So, I will short this DC bus. So, I cannot turn on S1, S2, S3 at the same time, right. So, therefore, I have to turn off S3 when I am turning on S1, and that is how S1 and S3 becomes complementary, and on a similar logic we can also find out that S2 and S4 are complementary. Okay. So, these two switches are always given complementary gate pulses. So, if I give a turn on signal for this one, I must give a turn off signal for S3, and S2 and S4 are again given complementary signals. Okay. So, this is what is also kind of like a summary. So, if I want to get Vd by 2 voltage, give pulses to S1 and S2, give turn on pulses or high pulses to S1 and S2. Okay. Again, depending on the direction of the current, either S1, S2 will conduct or D1, D2 will conduct. Okay. If I want to get 0 voltage between VAO, give high pulses to S2 and S3. Okay. And then if the current direction is positive, D5 and S2 will conduct. If the current direction is negative, S3 and D6 will conduct like this. If I want to get minus Vd by 2 voltage, give a high pulse to S3 and S4. Okay. And then I is positive means D3 and D4 will conduct, I is negative means this way it will conduct. Okay. And under all operating conditions, we maintain that S1 is complementary to S3, S2 is complementary to S4. Okay. Now, it is also possible in this converter to go from plus V d by 2 to minus V d by 2. Okay. If you see here the VAO voltage, we have switched between 0 and V d by 2 here, and then again 0 and minus V d by 2 here. But it is actually, you can also go from plus V d by 2 to minus V d by 2 directly, like from here to this state here. Okay. So, you are turning on S1 and S2 and immediately you flip it to S3 and S4. However, this operation is not done. Okay. It is primarily, this operation is avoided. We always go from plus V d by 2 to minus V d by 2 through a 0 level. Okay. Why? Because the main reason is the dV by dt is very high in this plus V d by 2 to minus V d by 2 case. So, no, this is not fully correct. So, I will write it in not like this, it increases the dV by dt, because when the voltage goes from plus V d by 2 to minus V d by 2 directly, then the whole DC bus, the total DC bus is the dV is the total DC bus, and so the dV by dt can be enormously high, okay, and that is detrimental to the operation of the converter, okay, or the operation of the, suppose the motor drive which is connected. So, we in case of neutral point clamped converter, we always go from plus V d to minus V d through 0. So, when we switch it, we go from plus V d by 2 to 0 and to minus V d by 2. Usually, always it is like this, or when it is going from minus V d by 2 to plus V d by 2, it goes through a 0 state. Otherwise, the dV by dt can be very high. Remember, this is a multi-level converter, and so the voltage can be, the DC bus voltage can be quite high, and so the dV dt can also be quite high for such a converter.